Section: Introduction. In this section, we discuss autoregressive models, ARMs, which predict the next tokens one at a time in a left-to-right manner. These models have been quite successful in natural language tasks due to their simplicity, allowing for rapid growth in model sizes. However, ARMs have notable limitations, particularly in complex reasoning and long-term planning, and they struggle with sequences that require meeting intricate constraints. Recently, masked diffusion models, MDMs, have emerged as a competitive alternative, addressing some of the shortcomings of ARMs. Yet, MDMs introduce new challenges, such as the risk of violating token dependencies when unmasking multiple tokens at once. For instance, if we fill in 2 tokens in the sentence, the chef added to the dessert to make it. Simultaneously, we might end up with nonsensical outputs. In contrast, filling them in one after the other leads to more coherent sentences. Additionally, MDMs depend on the number of masked tokens, which limits their effectiveness in arbitrary infilling tasks. For example, with the input, "the conference was postponed," the model cannot generate a more detailed version if only one token is masked. To tackle these issues, we introduce Insertion Language Models, ILMs. ILMs use a denoising approach where we drop some tokens from the input and learn to predict them one at a time. However, the naive approach to this can lead to high variance, making training difficult. To improve this, we propose an approximate denoising objective and a specific design for the denoising network. The main distinction between ILMs and MDMs is that ILMs completely remove the dropped tokens from the input and generate them sequentially, while MDMs replace them with a mask token. In our experiments, particularly with a synthetic task involving paths on a star graph, we find that ILMs consistently generate the correct paths, even when ARMs and MDMs struggle, especially with variable length paths. We also observe that ILMs outperform both ARMs and MDMs in challenging tasks like solving zebra puzzles. When trained on smaller text datasets like LM1B and tiny stories, ILMs show slightly better performance than MDMs in unconditional text generation and are competitive with ARMs. Furthermore, we demonstrate that ILMs effectively handle infilling of sequences of arbitrary lengths in a zero-shot manner. In summary, our key contributions include the introduction of Insertion Language Models, ILMs, that can insert tokens at any position in a sequence while managing strong dependencies. We present a neural network design and a straightforward denoising objective that facilitate ILM training. Our empirical evaluations show that ILMs outperform ARMs and MDMs in common planning tasks and are competitive in text generation, offering greater flexibility for arbitrary length text infilling compared to MDMs. Section Summary. In this section, we introduce Insertion Language Models, ILMs, which address the limitations of autoregressive models, ARMs, and masked diffusion models, MDMs, by learning to insert tokens at arbitrary positions while maintaining strong token dependencies. Our empirical evaluation shows that ILMs outperform ARMs and MDMs on planning tasks and are competitive in text generation, offering enhanced flexibility for arbitrary length text infilling. Section: Masked Diffusion Models. In this section, we discuss masked diffusion models, MDMs. We denote our token vocabulary as a finite set and define a probability mass function over sequences. We assume a fixed order for the tokens, allowing us to represent a specific token with an indicator vector that is 1 at its index and 0 elsewhere. We also include a special mask token with a probability of 0. The training goal for MDMs can be expressed as the expected loss based on data, where we consider the transition probability of the noising process and a learned denoiser that generates a probability distribution over the vocabulary for each position in the sequence. The noising function is a decreasing function that ranges from no noise to maximum noise. However, MDMs have limitations during inference. At a certain time step, we randomly unmask a subset of tokens, which can lead to incoherent outputs if too many tokens are unmasked at once. Additionally, the fixed number of masks between unmasked tokens restricts the flexibility of infilling lengths. To address these issues, we introduce the Insertion Language Model, ILM. ILM allows us to generate sequences of varying lengths and orders by inserting tokens one at a time. At each step, we predict an output token and its insertion position, with the option to stop when the sequence is complete. This model eliminates the need for placeholder mask tokens, avoiding the rigid constraints of MDMs and allowing for more flexible generation compared to left-to-right approaches. We view ILM as a denoising model that drops tokens instead of replacing them with masks. Training this model involves considering all possible paths that lead back to the original sequence, which we can achieve through Monte Carlo sampling. However, this can introduce high variance in loss estimates. To mitigate this, we adopt a biased training objective that directly utilizes all dropped tokens in a single gradient step. Our training objective consists of two components, one for token insertion and another for a binary decision on when to stop generation, which influences the sequence length. We define a set of bit vectors for the positions of dropped tokens and learn the insertion probabilities based on the original sequence. The second component involves training a binary classifier to determine if the sequence is complete. The overall training loss combines the token insertion loss and the stopping loss, with both components sharing the same transformer backbone and being trained together. During inference, ILM inserts tokens one at a time, and we can sample from the joint distribution or use two-step sampling methods for each step. Section Summary. In this section, we introduce masked diffusion models, MDMs, and highlight their limitations during inference, such as incoherent outputs and fixed-length constraints. We then propose the Insertion Language Model, ILM, which generates sequences by inserting tokens at arbitrary positions, allowing for flexible sequence lengths and improved coherence by avoiding the use of mask tokens. Section: Parameterization. In this section, we parameterize the model using insertion logits calculated from a standard transformer. We denote our transformer backbone as a series of transformer layers, excluding the final unembedding layer. For each position in the sequence, we take the output from the transformer backbone and pass it through the unembedding layer to obtain the insertion logits. These logits represent the unnormalized log probability of inserting a specific token between two positions in the sequence. The overall distribution for all possible insertions is then established. We predict the stopping probability using the output from a special token that we always place at the start of the input sequence. In the related work, we note that diffusion models have become a strong alternative to autoregressive models, ARMs, for tasks that require planning and adherence to constraints. Masked diffusion models, MDMs, have shown competitive scaling with ARMs while addressing some of their limitations. However, due to fixed-length mask tokens and simultaneous unmasking, MDMs can generate incoherent sequences without additional inference techniques. Some approaches, like using a greedy strategy for token selection or introducing stochasticity, aim to improve sample quality during inference. Others modify the MDM training objective to help the model focus on critical sequence parts, but this has only been effective for synthetic tasks. We propose a new parameterization and training objective that differs from existing methods. While MDMs can denoise an entire sequence at once, order-agnostic models generate one token at a time in any order. Our model generates sequences by inserting tokens at arbitrary positions, allowing for more natural infilling compared to ARMs. Few works have tackled arbitrary length infilling with ARMs, often requiring specialized fine-tuning. One approach trains ARMs to generate a middle part of a sequence given a prefix and suffix, but it struggles with arbitrary infilling. Another method adapts pre-trained ARMs to masked denoising models, but it inherits the same limitations as MDMs. For our empirical evaluation, we examine the differences between Insertion Language Models, ILMs, MDMs, and ARMs through two planning tasks: a generalized synthetic planning task on star-shaped graphs and zebra puzzles. We also assess ILM performance in unconditional text generation and infilling, training on two distinct language modeling datasets, the 1 billion word benchmark and tiny stories. In all experiments, We utilize a transformer architecture with rotary position encoding for ILMs and ARMs. For MDMs, we employ the DDIT architecture, which incorporates adaptive layer normalization in the transformer to condition on the time variable. MDMs have slightly more trainable parameters than ILMs due to this additional component. Section Summary. In this section, we parameterize our model using insertion logits from a transformer backbone, which generates unnormalized log probabilities for token insertions in a sequence. We also discuss the limitations of existing masked diffusion models and autoregressive models in infilling tasks, proposing a new approach that allows for more flexible token insertion and demonstrates its effectiveness through various empirical evaluations. Section: Star Graphs. In this section, we focus on the key features of three models by examining the task of generating a path from a starting node to a target node on star-shaped graphs. A star graph consists of one central junction node. We create three task versions: Star-EC, which includes symmetric graphs where the start node is always the junction node, and all paths are equal in length; Star-Medium and Star-Hard, which feature asymmetric graphs with varying arm lengths, where the start node is not the junction, and there are both incoming and outgoing edges from the junction. The easy, medium, and hard datasets have graphs with degrees of 3, 2, and 5, respectively, and maximum path lengths of 5, 6, and 12. We present each graph to the model as a string of edges in random order, requiring the model to predict the path from the start node to the target node. All three models undergo training for 50,000 steps with a learning rate of 0.0001 and a batch size of 64. For StarSmall, generating the solution in reverse order, from target to start, proves optimal, as it simplifies dependencies. An autoregressive model trained in reverse achieves 100% accuracy on Star-EC but struggles with the original left-to-right order due to the need for look-ahead. Both the MDM and ILM can generate out of order and achieve 100% accuracy on Star-EC. However, the MDM's accuracy drops significantly on Star-Medium and Star-Hard, while the ILM maintains strong performance across all task variants, demonstrating its flexibility with variable lengths. Next, we discuss zebra puzzles, which are popular logic puzzles used to evaluate constraint satisfaction systems. We utilize a version characterized by a tuple where the first number indicates the number of entities and the second number indicates the number of attributes for each entity. The goal is to place each entity attribute pair in houses while satisfying given constraints. There are 7 types of relationships, including same house, different house, left of, immediate left, neighbor, ends, and between. To ensure consistency, we adopt the same setup and dataset as previous work. We train a transformer model with 42 million parameters, consisting of 8 layers and 8 attention heads, using rotary position encoding. The order in which we solve the constraints significantly impacts the model's performance. To illustrate the benefits of out-of-order generation, we train the model on output strings that present solutions in a fixed order sorted by house and entity. The ILM model achieves a sequence accuracy of 90%, surpassing both the MDM and ARM, and approaches the performance of the ARM trained on an Oracle solver's decomposed sequence order. Section Summary. In this section, we explore the generation of paths in star graphs through 3 task variants: Star-EC, Star-Medium, and Star-Hard, which differ in graph symmetry and arm lengths. We also discuss zebra puzzles, highlighting our transformer model's performance in solving these puzzles with out-of-order generation, achieving a sequence accuracy of 90% with the ILM model, surpassing other models. Section: Language Modeling. In this section, we evaluate our model's ability to generate both short and long text sequences using 2 small pre-training datasets with distinct features. 1. The 1 billion word benchmark, which consists of short news text sequences, and 2. A combination of tiny stories and ROC stories, which are designed for young children and contain common-sense narratives. The LM1B dataset includes short sequences of up to 2 to 3 sentences, while Tiny Stories has 2.1 million stories suitable for 3 to 4-year-olds, and ROC Stories adds diversity with 5-sentence stories. Together, these datasets provide us with 2.2 million stories for training. We train our models, ILMs, MDMs, and ARMs, using the same architecture, specifically a rope-based transformer, with around 80 million trainable parameters. We utilize a tokenizer to prepare the data, padding LM1B examples to 128 tokens and tiny stories to 1024 tokens. Our training involves an effective batch size of 512, with different training steps for each dataset, using the AtomW optimizer at a constant learning rate. For generating text without conditions, we apply different sampling methods, tau leaping for MDMs and nucleus sampling for ARMs. For ILMs, we use a two-step process involving top case sampling followed by nucleus sampling. We assess the quality of the generated text using metrics like per-token negative log likelihood, NLL, and entropy, calculated based on token probabilities and their frequencies. We also employ a large language model, Prometheus 2, to evaluate various aspects of text quality, focusing on coherence and grammar. Our findings indicate that both MDM and ILM have worse NLL compared to ARM, likely due to differences in training efficiency. However, ILM outperforms MDM in NLL across both datasets. While ILM shows lower token diversity compared to MDM and ARM, it still remains close to the dataset's entropy. We observe that MDM generates longer sequences, contributing to its higher entropy, but struggles with coherence, especially in longer narratives. In contrast, ILM maintains a balanced linguistic output and consistently surpasses MDM, which particularly falters in the stories dataset as the length of generated text increases. Additionally, MDM uses a fixed number of input tokens during inference, while ILM starts from 0 and increases to the maximum length. We also analyze how the time taken for each token generation affects quality, noting that while MDM's quality improves with more sampling steps, it still lags behind ILM. Section Summary. In this section, we evaluate our model's ability to generate text using two datasets: the 1 billion word benchmark for short news sequences and a combination of tiny stories and ROC stories for longer narratives. Our findings indicate that while the MDM generates longer sequences, it struggles with coherence compared to the ILM, which produces linguistically balanced outputs and performs better in terms of negative log likelihood, especially in the context of the stories dataset. Section: Infilling. In this section, we construct an infilling evaluation dataset using 3,500 test sequences from the LM1B dataset. We create a single segment version by removing one continuous segment of tokens from each example, and a multi-segment version by removing two or more segments. For the tiny stories dataset, we build a single segment infilling evaluation set by taking the first 3,300 examples and removing the middle sentence from each. Since we want to assess how well pre-trained models can perform infilling, we only compare masked diffusion models, MDMs, and insertion language models, ILMs, as autoregressive models, ARMs, cannot infill without special training. We use negative log likelihood, NLL, and entropy as our evaluation metrics. To evaluate the quality of the infilled text, we look at the percentage change in NLL or entropy, comparing the input with missing segments to the ground truth text. When we provide the evaluator model with the input text, the tokens from the removed segment are entirely omitted. Thus, we expect to see a decrease in NLL for the input text and an increase when compared to the ground truth. Our results show that the ILM outperforms the MDM across all three evaluation datasets in terms of NLL. In the tiny stories evaluation, both models show an increase in NLL compared to the input text. However, upon reviewing the stories, we find that they are often simple, and removing a middle sentence does not significantly alter the overall meaning, resulting in a low NLL for the input sequences with missing segments. In this paper, we introduced Insertion Language Models, ILMs, which learn to insert tokens at any position in a sequence, addressing the limitations of both ARMs and MDMs. By inserting one token at a time and allowing for any generation order, ILMs effectively manage strong token dependencies without being limited to left-to-right generation. We achieve successful training through a specialized network setup and a denoising objective that approximates a distribution over denoising steps. Our experiments show that ILMs outperform ARMs and MDMs in planning tasks, perform similarly to ARMs in unconditional text generation, and excel in arbitrary length text infilling compared to MDMs. While ILMs demonstrate promising results in synthetic planning tasks and language modeling, they do have limitations. Specifically, ILMs perform slightly worse than ARMs trained for the same number of gradient steps. Like MDMs, ILMs do not allow for caching hidden states, making them slower at inference compared to ARMs that utilize hidden state caching. Addressing these issues and scaling ILMs to larger datasets are key areas for future research. For reproducibility, we provide details about the network, datasets, architecture, and training hyperparameters in the empirical evaluation section and the appendix.